Hello and welcome to Acoustics 1. This is the first of two webinars covering acoustics. Today we'll discuss how manufacturers test and rate air distribution devices such as terminal units and diffusers for acoustical performance. My name is Randy Zimmerman and I'll be presenting today's program. I'll be joined later today by Jim Oswegen and David Pick for the question and answer portion of today's program. Jim is a chief engineer at Titus with 47 years of HVAC experience, and David comes to Titus with over 15 years of experience as a consulting engineer. You may submit your questions at any time during the webcast, and we will answer them for the benefit of all in attendance at the conclusion. We'll discuss what sound is, how it is measured, and the difference between sound power and sound pressure. We'll also look at sound quality and the industry standards that are used to test and rate the acoustical performance of air outlets and air terminals. In order to determine the sound power performance of a product, tests must be conducted in a controlled environment. There are two types of sound rooms, reverberant chambers and anechoic chambers. In our industry, all products are tested in reverberant chambers because this is the ideal environment for testing quiet products that tend to make humming, hissing, or rumbling noises. A properly designed and constructed reverberant chamber should provide isolation from environmental noise and vibration while creating a space with the lowest possible sound absorption. In the reverberant chamber, sounds bounce around the room, thereby eliminating all directionality from the sound source. The resulting sound environment is known as the reverberant field. In a properly qualified reverberant chamber, sound levels should be equal at all locations in the reverberant field. Sound levels are then measured using either a single microphone on a rotating boom or an array of microphones suspended from the ceiling. Sound power cannot be measured directly, so it is necessary to use the comparison method to calculate sound power from sound pressure readings. All readings taken with microphones are sound pressure readings because microphones are simply high-speed pressure transducers. The difference between sound power, the total sound energy produced by the item under test, and sound pressure, the resulting room sound level, is called room effect, room absorption, or attenuation. We can determine the room absorption by measuring the sound pressure of a reference sound power source called an RSS. Since the sound power of the RSS is known, any difference between it and the measured sound pressure must be attributed to room absorption. This room absorption is a constant that can be applied to sound levels of any magnitude. In order to get meaningful results, there's a procedure that must be followed during the sound testing process. First, we must set up all the ductwork and equipment to be tested. Any unnecessary material should also be removed from the test chamber because everything inside the chamber will absorb some amount of sound energy. Material must not be moved in and out of the chamber between test runs, as this will change the room attenuation each time it occurs. Next, we must determine the background sound pressure level after turning off all the equipment and closing the sound chamber doors. It's important to know the background level in order to avoid background interference. So long as all readings are at least 10 dB above background level, no interference will occur. Next, we switch on the reference sound source and measure its sound pressure level. If it is known to produce 80 decibels of sound power in a given octave band, but only 70 decibels of sound pressure is measured, we know that the room attenuation in that octave band equals 10 dB. We can now switch the RSS off and start our sound test. Each unit under test will be run at various speeds, pressures, and flow rates in order to determine its acoustical performance over the full operating range. The next thing we need to talk about is the decibel, or dB. We don't need to know a lot about it other than its reference to a very low power and a very low pressure. It's also important to know the frequencies of decibel levels when discussing acoustical performance. Although there are an infinite number of frequencies, for simplicity, the entire audible sound spectrum has been divided into 8 equal bands known as the octave bands. Each band is defined by its center frequency. The first band is centered on 63 Hz and the second band is centered on 125 Hz. You can see that the center frequency doubles until we reach the 8th band centered on 8000 Hz. Obviously the first band represents low frequency sound and the 8th band is high frequency sound. This grouping of frequencies provides the acoustician with a shorthand way to discuss sound quality and the effect of various sound contributions to the overall resulting sound level. Certain octave bands are critical to the overall performance of certain products. Fan-powered products, including fan boxes, room fan coils, and air handlers, typically create their highest sound levels in the second octave band, occasionally shifting to the third octave band as fan speed increases. Grills, registers, and diffusers typically create their highest sound levels in octave bands 4 through 6, most commonly peaking in the 5th octave band. These 3 octave bands have the special distinction of being known as the speech interference bands. That's because these bands occupy the same portion of the audible sound spectrum shared by human speech. For this reason, rooms with noisy diffusers are also very poor for speech communication. Although manufacturers record sound data in bands 1 through 8, it is an industry convention to only report data in bands 2 through 7. Some sound chambers have difficulty with first band measurements due to the size limitations because low frequency sounds involve long wavelengths. Other sound chambers have difficulty with 8th band measurements when the room is large and humidity may be difficult to control. You might be surprised to know that high frequency sound can be absorbed by moist air. Now let's talk about how sound sources can be added because we are rarely dealing with a single source in isolation. If we have 2 sound levels and we assume that they are in the same octave band, what's the total sound? Do you think we can just add them up directly? No, of course not. That would be too easy. In order to add these 2 decibel levels together, we must take the difference and then either use logarithmic math or a chart like the one on the left side of the screen. It tells us that for a difference of 6 decibels, we must add 1 decibel to the higher of the 2 sound levels. That means that 80 plus 74 equals 81 decibels. You probably wouldn't have figured out that one without a little help. There are a couple other interesting things that we can learn from the chart. For instance, what if we want to add 80 plus 80 decibels? That would be a difference of 0, so the chart tells us to add 3 decibels, making the total 83 decibels. This is a handy rule for doubling sound sources. Just add 3 decibels. What happens if we want to add 80 and 70 decibels? That would be a difference of 10 decibels, so the chart tells us to add 0.4, making a total of 80.4 decibels. If we then round to the closest decibel, we're back to 80 dB. This explains why sound readings should always be at least 10 dB higher than background levels in order to avoid interference. So we come away with 2 good things to know. When there's a difference of 10 or more decibels between sound sources, they're no longer additive. Whenever you want to know the effect of doubling sound sources, just add 3 dB or roughly 3 NC. This works for similar products that create similar sound spectrums like 2 diffusers, 2 fan boxes, or a diffuser and a grill. 2 NC40 boxes over a single office would probably sound like NC43, and 2 NC20 diffusers in a small room would likely result in NC23. Don't try to add up dissimilar products this way, or you'll get the wrong answer. These are good things to know. Now let's look at multiplication. Sound sources can be multiplied by taking the log of the multiplier, multiplying it by 10, then adding it back to the original sound level. For instance, if we know that 1 fan sounds like, but we want to know what 2 fans sound like, we take the log of 2, which is 0.3, we multiply it by 10, and that means we have to add 3 dB. That's exactly what we found in the previous exercise. If we want to know what 4 fans sound like, we add 6 decibels. For 10 fans, we add 10 decibels, and so on. If we know what 50 fans sound like and we want to know what 100 fans sound like, we're back to adding 3 dB because we're doubling the original sound source. This leads us into a discussion about proximity to sound sources. Would you really expect to hear 100 fans running at the same time? They would need to be extremely small fans in order to be heard from a single listening point. There's a rule of thumb that says properly selected diffusers should not be heard when they're more than 10 feet away from the listener. So if we have two NC20 diffusers that are more than 10 feet apart, it's unlikely that we'll hear both from any single location. It's important to understand that in large spaces with multiple diffusers, possibly high in the air, we don't need to concern ourselves with the additive effect of multiple sound sources. In these spaces, the distances are too great, and the room volume also acts to absorb what little sound they may create. For the same reason, we say that it shouldn't be possible to hear any more than a 10-foot section of continuous slot diffuser. Manufacturers' catalogs often provide corrections for lengths from 2 to 10 feet for this reason. Although in some instances, a long slot with alternating active and inactive sections could stretch hundreds of feet, we can likely only hear the nearest 10-foot section. Our ears aren't perfect listening devices. When it comes to high-frequency sound, a difference of 1 decibel in sound level is not noticeable, and a difference of 3 dB is just perceptible. However, we can easily distinguish a difference of 5 dB. A difference of 10 dB sounds twice as loud, and a difference of 20 dB sounds 4 times as loud. This means that 90 decibels sounds twice as loud as 80 decibels when we're talking about our perception of high-frequency sound. It's safe to say that we are twice as sensitive to low-frequency sound than we are to high-frequency. That's why low-frequency sounds generated by motors and blowers are the most frequent cause of noise complaints. It only takes 3 dB of low frequency to be noticeable, 5 dB sounds twice as loud, and 10 dB sounds 4 times as loud. In terms of NC, we can say that for a fan-powered product, an NC35 unit sounds twice as loud as an NC30 unit. Not only is our hearing non-linear, but we also have difficulty judging sound levels at different frequencies. For instance, 65 decibels of low-frequency sound sounds equally loud as 40 decibels at a higher frequency, even though there's a difference of 25 dB. In other words, it's safe to say that in order to assign a loudness to a sound level, instrumentation must be used. We cannot rely on our ears because our perceptions are not accurate or repeatable. Although we cannot reliably determine sound levels, our ears and our perception are very good at identifying both pleasant sound environments or picking out annoying sounds in a room. Now let's take a look at acoustic quality. According to AHRI, we don't want a space to be too quiet. Now that may not make sense at first, but what they're talking about is typical office spaces shared by multiple workers. If these spaces are too quiet, there's a loss of speech privacy. The ability to hear multiple conversations going on between workstations often results in an unproductive environment. A slightly louder background level can allow employees to speak at normal levels without disturbing their neighbors. Obviously, we don't want a space to be too loud. We also don't want anything annoying to the occupants, such as fans that cycle on and off or sounds that change in loudness or tone. This is the reason why some engineers don't like to specify parallel fan-powered terminals. Although the parallel fan typically handles half the air of a series fan, the fact that it cycles on and off for heating makes it noticeable and therefore annoying. Now the last one is the scary one. We don't want any sounds that can be felt. They are referring to low-frequency rumble that can cause vibration. This typically creates an oppressive environment that most people would not enjoy. These are the NC or noise criteria curves. These curves were developed many years ago based on the hearing response of adults to various sound levels and frequencies. You'll see that the vertical axis shows the sound pressure levels in decibels, and the horizontal axis is marked by octave band center frequencies. The sweeping curves on the chart show the maximum allowable sound pressure levels for a given noise criteria. You'll notice that the curves are shown for NC levels in increments of 5 points, but there are actually an infinite number of possible NC curves. The lowest curve shown is NC15, and that's generally accepted to be the threshold of hearing for a healthy adult. There's nothing magical about showing NCs in increments of 5, but as a practical matter, most acoustical specifications will designate different sound levels in various spaces in increments of no less than 5 NC points in order to create environments that are audibly different from one another. The NC levels specified for spaces in office buildings typically range from NC30 to NC45. The quietest spaces are usually conference rooms specified not to exceed NC30. It can be difficult to get sound levels lower than NC30 without adding additional soundproofing to a structure. Why is the conference room the quietest space? We must always remember that the sound level in any room should match the purpose of the space. Conference rooms are intended to facilitate meetings and discussions, so a low background level is helpful. The next loudest space would be a private office specified not to exceed NC35. This gives a supervisor or manager a good environment for meetings with employees, talking on the phone, reading and writing. The ability to close a door for additional sound reduction and privacy means that nothing special in the way of equipment is typically required beyond that serving the louder adjoining spaces. Open office areas furnished with cubicles or open workstations are most productive when sound levels are as close to NC40 as possible. This seems to provide the best speech privacy. Hallways and restrooms are transitory spaces, so higher sound levels are acceptable there. In restrooms, exhaust fans often provide excellent sound masking of things that nobody really wants to hear. Since diffusers tend to create sounds that are hard to talk over, it's a good idea to select diffusers for an NC level at least 10 points lower than the room they serve so that they will not be heard. It's important to understand the difference between sound power and sound pressure. Sound power is the raw sound energy generated by a system or device. Sound pressure is the sound level measured in a space. The difference between the two is known as attenuation or room effect. The only way that sound pressure could ever be equal to sound power would be in an environment that provided no sound absorption or attenuation, and no such place really exists. We cannot measure sound power directly. We can only measure sound pressure and then add back the room attenuation in order to calculate the sound power. AHRI standard 250 defines the reference sound source, or RSS. This device is calibrated in an anechoic chamber to simulate a free field environment, but for our purposes is tested in a reverberant chamber. It therefore has a known error called the environmental effect that must be corrected in our calculations. To summarize what we've covered so far, in Reverb Room testing, we calculate the sound power generation of a device by measuring the sound pressure and adding the room attenuation. We determine room attenuation by comparing the measured sound pressure level of the RSS to its published sound power level. This effectively calibrates the test chamber. And we know we should try to keep the sound readings at least 10 decibels higher than the background level to prevent background interference. Data is generally recorded in octave bands or 1/3 octave bands when checking for pure tones. When testing to produce catalog data, manufacturers typically use a frequency analyzer to read the sound pressure levels from a microphone array. These sound pressure readings are corrected to sound power readings by adding the previously determined room attenuation back in. The resulting data is regressed in order to determine the coefficients of the equations that describe the data set. These equations and coefficients can then be used to calculate catalog data for any operating point within the recommended operating range. These same equations can be used in selection software to model the performance of a product. The proper method for testing grills, registers, and diffusers is defined in AHRI Standard 70. The current version was adopted in 2006. There have been no significant changes in sound testing procedures for many years. The proper method for sound testing terminal units is detailed in AHRI Standard 130. The current version was adopted in 2008 and is currently under review by AHRI SPC 130. The standard will soon be expanded to include test procedures for exhaust terminals. There's currently no standard test procedure for exhaust terminals, so there's no current standard for rating their performance or presenting catalog data. Sound tests conducted in reverberant rooms typically fall into three different types. There's discharge sound for terminal units. In this test, the unit is suspended outside the chamber with a discharge duct terminating flush with the inside wall. This test is used to determine the sound of air discharging from a blower or a damper. Radiated sound testing requires that the terminal unit be hung in the center of the room, with all supply and discharge ductwork wrapped with lagging material to prevent noise breakout. We only want to measure the sound radiating from the unit casing and not the contribution of the ductwork. Grills and diffusers are mounted on the end of a large pressurized plenum that ends inside the chamber. Products that are designed to be ducted must be fitted with a short stub duct and a bell mouth transition before mounting them on a plaque at the end of this plenum. This is done to create a non-turbulent neck condition to simulate a ducted connection. The same setup can be used for testing both supply and exhaust devices by simply reversing the direction of airflow. The current rating standard for terminal unit performance is AHRI Standard 880. The 2011 version went into effect on January 1st of 2012. This standard tells manufacturers how to present performance data measured in accordance with AHRI Standard 130 and also details the rating points that must be used when participating in the voluntary AHRI Directory of Certified Performance. This is an important program intended to improve the accuracy and reliability of manufacturers' data. The biggest change introduced in this standard involves end reflection. End reflection occurs when airflow undergoes rapid expansion or contraction. This commonly occurs when air discharges from an outlet. Air that was confined by ductwork suddenly expands to fill a room. When this occurs, a certain amount of sound energy is reflected back towards the source rather than traveling to the room. This is sound energy that cannot be read by the microphones in the test chamber, but it must be accounted for. An AHRI research project, RP1314, completed in 2008, provided a means of calculating end reflection based strictly on the discharge duct dimensions. According to this latest standard, all manufacturers must calculate end reflection and add it to the discharge sound power levels of all terminal units. This will effectively increase sound levels on all types of terminal units, with the most effect on smaller units. This happens because the smaller the discharge duct is, the greater the end reflection will be. Larger units will see little to no change. The current standard for estimating sound levels in a space is AHRI Standard 885. This standard is unchanged from the previous AHRI Standard 885. It provides numerous tables of data, mostly resulting from AHRI research, that can be applied to estimate both radiated and discharge sound paths. Familiarity with these tables is generally needed in order to properly apply the attenuation factors. Like all AHRI standards, this standard is available for free download from their website at www.ahrinet.org. Standard 885 contains a very important section called Appendix E. This was first introduced in AHRI Standard 885-98, and it established the standard attenuation values that all manufacturers should use to calculate catalog NC values. Prior to the adoption of this standard, it was very risky to compare NC values from one manufacturer to another. It often meant reading and understanding all of the fine print concerning how exactly the NC values were determined. For this reason, it was usually best for engineers to only compare sound power levels when making performance comparisons. Now it is much less risky, but it's still important to remember that the typical sound paths recommended in Appendix E may not closely match actual job site conditions. These are the standard catalog attenuations that Appendix E recommends for terminal unit applications. You can see that the radiated sound path is very simple. It takes a deduction for the environmental effect and a combined ceiling space effect based on the type of ceiling used. Your actual ceiling may be better or worse, or you may have no ceiling at all. If that's the case, adjustments must be made to accurately estimate the resulting sound level in the room. The radiated sound path is more complicated because it includes more possibilities. While there's always an environmental effect, we now must consider duct lining, end reflection, flex duct, and space effect. In addition, more adjustments due to duct sizes and division of flow between multiple rooms are taken based on air volume. If your actual job site conditions will involve unlined ductwork or won't include flex duct, these deductions shouldn't be taken. Appendix E was developed by industry professionals to simply provide standardization between manufacturers' data as an aid to engineers and designers wanting to make quick comparisons. For that intent, it serves its purpose well. AHRI administrates a voluntary program called the Directory of Certified Performance for terminal unit products. The rating points come from AHRI Standard 880. Although these rating points may not be typical operating points for the products, they are chosen as good repeatable test points. The purpose of the program is to hold participating manufacturers responsible for the accuracy of their published performance data. The program requires third-party verification tests conducted at an independent laboratory at the manufacturer's expense. AHRI randomly selects unit models and sizes taken from each manufacturing location for annual check tests. Any units that fail to perform within established test tolerances can result in additional tests, mandatory re-rating, monetary fines, and possible ejection from the program. Occasionally, customers ask why manufacturers don't include A-scale, A-weighted, or dBA sound in their catalogs. There's nothing wrong with dBA sound, but it provides less information to the engineer than octave band sound power levels. A-weighted sound averages all of the octave bands together to produce a single number rating. dBA sound meters are inexpensive and readily available. They're often used by code officials to measure environmental noise levels or by OSHA inspectors to determine whether or not hearing protection is needed inside a manufacturing facility. Although dBA ratings have their uses, octave band readings provide better clues as to the source of a noise problem and therefore are more likely to lead to a possible solution. So this concludes Acoustics 1. Hopefully we've clearly explained the difference between sound power and sound pressure and explained why NC levels should always match the use and purpose of an occupied space. We covered the standards and procedures that are used by manufacturers in order to create catalog performance data for products like air outlets and air terminals. We also discussed the standards that govern performance rating and performance certification. Next month, Acoustics 2 will cover best practices when writing acoustical specifications and look at recommendations for quiet products related to optional features like lining materials, optional attenuators, and good installation techniques. I want to thank you for joining us. We'll now turn it over to our panelists to answer any questions that we've received during the course of this program. Thanks again.